In this video, I am going to explain algebraic operations on complex numbers. First, let us see scalar multiplication of complex numbers. A complex number can be represented like this: x plus I, y. And k is a scalar belonging to real numbers. If the complex number z is multiplied by k, then both you have to multiply real part and imaginary part. So x will become kx and y will become ky. Now suppose scalar is 0. So 0 into z is 0. Suppose the scalar is 1. So 1 into z is z. Here scalar is minus 1. Minus 1 into z is minus z. Here three examples are given. Here real part is marked along the x-axis and the imaginary part along the y-axis. This point is representing the complex number x plus iy. So this is x and this is y. So this point will represent this complex number x plus iy. In the first example, k is 2. So this complex number z is multiplied by 2, it will become 2z. So if this is representing z, this will represent 2z. A complex number can be represented by a vector also. So this is representing z. So this is representing 2z. Here k is 1 by 2. So this is representing z. So this is representing 1 by 2z. This point is representing 1 by 2z. Here k is minus 1. So this is representing z. So this is representing minus z. Minus z will be in the third quadrant. This is z. This is minus z. Next algebraic operation is addition of complex numbers. Two complex numbers are given. z1 is equal to x1 plus iy1. z2 is x2 plus iy2. Now z1 plus z2 is x1 plus iy1 plus x2 plus iy2. In this x1, y1, x2, y2, they are real numbers. So when you add, we have to add this real part first, x1 plus x2 plus y1 plus y2. It can be represented like this. z1 can be represented by this point. It is x1 plus iy1. So this is x1 and this is y1. Or it can be represented by this vector or a vector. Then z2 is represented by this point. Its real part is x2 and the imaginary part is y2. Then a vector is characterized by its magnitude and direction. It is unaltered if it is shifted. Without rotation, if it is under translation, it is not changing. So this is shifted here. Now z2 is represented by OB vector. Then a vector is characterized by magnitude and direction. Under translation, there is no change. Now this point will represent z1 plus z2 or this vector OC vector. OC vector, so according to the parallel law of vectors, if two vectors are represented by the two sides of a parallelogram, so diagonal will give you the resultant. So you can apply parallelogram law of vectors. If this is representing z1 and this is representing z2, z1 plus z2 is represented by this point or this vector, OC vector. Now subtraction of complex numbers. z1 is x1 plus iy1, z2 is x2 plus iy2. Now z1 minus z2. Here z1 is x1 plus iy1 minus then x2 plus iy2. So here you have to subtract real part separately and imaginary part separately. So x1 minus x2, then plus I common taken outside, then y1 minus y2. You have seen how to add two complex numbers. If this is z1 and this is z2, then if you complete this parallelogram, this will represent z1 plus z2. Now we have to subtract z1 minus z2. z1 minus z2 is same as z1 plus negative of z2. If this is z2, this is negative of z2. You extend it backwards, same length. So this is minus z2. Now you complete this parallelogram. This is z1, this is z2, minus z2. So you complete this parallelogram. Then this will give you z1 plus minus z2. That means it is this point will give you z1 minus z2. I hope you have understood the addition and subtraction and scalar multiple of a complex number. Thank you for watching the video.